This presentation describes the use of petroleum stratigraphy using GORE sorber technologies and its application to drilling efforts. This project was a joint effort between Merty Energy and GORE and Associates. GORE would like to thank Dr. Kadir Gürgey and Tuba Sökmensüer of Merty Energy for their efforts in processing and interpreting the data for this project. Petroleum stratigraphy may be used in many ways. It can be used to select and rank the most effective pay zone test intervals, examination of vertical reservoir compartmentalization, detection of vertical migration fronts, can be used to predict reservoir fluid types, prediction of hydrocarbon maturity, differentiate thermogenic and biogenic gas, as well as evaluate reservoir alternation processes like water washing and biodegradation. For this project, cutting samples were collected at the shaker table every 15 minutes from 18 meters to 1843 meters. The cuttings were rinsed, dried, and transferred to GORE sample jars. Upon completion of the drilling activity, the cutting samples and related field QC samples were shipped to GORE's laboratory in the U.S. for analysis. Once in the GORE laboratory, the samples were exposed to GORE's proprietary sorber module to absorb the hydrocarbons from the samples. The modules were then analyzed at part per billion levels using thermal desorption GCMS analytical methods. While the methods measure compounds from C2 to C20, including pristane and phytane, due to evaporative losses, actual compound detection normally begins at C6 for this application. It should be noted that traditional solvent extraction methods normally lose the light ends during the extraction process and do not begin compound reporting until C13. Also, the qualitative and quantitative results reported by traditional methods vary based on the solvent used for the extraction process. Since the GORE methodology uses thermal desorption instead of solvent extraction, it is unique in reporting compounds in the C6 to the C13 carbon range. Only naturally occurring petroleum compounds were chosen by Merty Energy for their evaluation, thus reducing the total number of compounds from 88 to 45 for this project. Upon completion of the analysis, the data were evaluated using multivariate statistical analysis to evaluate oil-to-oil relationships of the various intervals. It is very important to note that water-based drilling muds were used for this project. The use of oil-based drilling mud, such as diesel, would contaminate the analytical process and prevent the differentiation of naturally occurring hydrocarbons from drilling mud additives. It should also be noted that all interpretation of these results have been performed by Merty Energy. This graph plots the summation of C1 through C5 in total nanograms versus depth. The red numbers on the graph represent the sample ID. From 0 to approximately 500 meters, there is little gas response. From 500 meters to 1500 meters, the values fluctuate from approximately 0 to 2000 nanograms, indicating essentially a background level. However, from 1500 to 1750 meters, the values dramatically increase to a maximum of approximately 3500 nanograms, indicating potential light gases in this zone. This graph plots the summation of C6 through C20 in total nanograms versus depth. From approximately 1000 to 7000 nanograms of fluctuation, one can see between 500 meters and 1500 meters a background level. These values increase substantially at 1500 to 1750 meters to a maximum of about 49,000 nanograms, indicating the potential presence of higher hydrocarbons in this zone. Since this methodology includes in excess of 88 compounds, any number of compounds can be plotted individually versus depth to evaluate a variety of factors. For example, pentane can be used as a gas indicator. Decane versus depth can be used as an oil indicator, while benzene can be used as a proximity to pay indicator. These are just an example of many of the plots that can be used. Evaluation of pay zones. This graph plots the response of the summation of 40 oil-specific compounds versus depth. The blue dashed line, horizontal line, indicates the background level. The background level was calculated as the mean plus 1/2 the standard deviation of all the samples. That value is approximately 8,040 nanograms. The figure also suggests that the most promising oil intervals for this well are between 1550 meters and 1740 meters. The significant drop in hydrocarbons between 1620 meters and 1635 meters suggests potential compartmentalization, indicating 2 hydrocarbon zones or intervals rather than just one. While this compartmentalization might be missed on logs or other traditional methods, it can be detected with this methodology due to part per billion sensitivity of the technology. The possibility of a seal between interval A and interval B are also supported by an inspection of the hydrocarbon fingerprints obtained from the samples from zone A and B. The figures here represent the chromatographic data from the GORE modules showing compound intensities for ethane through phytane. First of all, it should be noted that both fingerprints are indicative of oil signatures as proposed by the previous graphs. Secondly, there are distinct differences between the two oil fingerprints, supporting the supposition of compartmentalization between interval A and interval B. Let's discuss oil-to-oil correlations using multivariate statistical analysis. With the availability of data for 45 petroleum compounds for this project, a robust statistical analysis could be performed on the data. For this case study, 24 compound ratios were evaluated for the samples designated in the hydrocarbon intervals A and B as shown on this graph. This graph shows the plotting of all of those compounds and the ratios, as you can see C16 to C17 and a variety of other multivariate responses. This graph shows the results of the statistical analysis. The box on the right indicates the sample's ID and the depth at which these samples were collected. First of all, note that the 3 samples, 107, 108, and 109, that were previously identified as possible seals were statistically clustered together as indicated by the purple box on the chart. In the upper level, interval A, the statistical analysis indicates that samples 101 and 102 at 1515 meters and 1530 meters had similar oil chemistries as did samples 103 and 104, and samples 105 and 106. The data also indicated that samples 112 and 113 had similar oil chemistries, and samples 115, 16, and 17 were also grouped together. More importantly, it should be noted that the list of compounds provided here can be used in geochemical interpretive charts to indicate many factors such as depositional environment, thermal maturity, biodegradation, and water washing. In conclusion, this technology is very useful for identifying potential pay zones. Due to its part per billion detection levels, it can identify potential pays missed by other technologies as well as possible migration pathways. Due to the fact that this technology measures from C2 to C20, it clearly and definitively can identify the hydrocarbon phase, be it gas, condensate, or oil. To date, this is the only technology that provides data for the C6 and C13 carbon range. This carbon range is missed by traditional methods that use solvent extraction. Additionally, since this technology uses thermal desorption, the hydrocarbon fingerprint is more closely resembled of those whole oil fingerprints detected for hydrocarbons. So, solvent extraction methods discriminate significantly on the hydrocarbon fingerprint based on the solvent of choice. With the extensive compound list of 88 compounds, explorationists easily compare compound ratios to evaluate oil-to-oil comparisons and oil-to-source rock comparisons. This information can be exported to standard geochemical interpretive plots to evaluate a variety of issues such as depositional environment, thermal maturity, kerogen type, possible biodegradation effects, water washing effects, and many others. Additionally, these data can be used to evaluate hydrocarbon correlations field-wide. Such information can be invaluable in assessing producing zones field-wide and what zones may be best for completion in the future. Examples in this case study clearly show the ability of this technology to assess vertical reservoir compartmentalization. Additionally, due to its sensitivity, this technology can potentially detect compartmentalization that may not be evident on well logs. Obviously, reservoir compartmentalization can have a dramatic impact on well completion efforts and cost and the future production capabilities of a well. Aromatic compounds like benzene, toluene, and ethylbenzene are very water-soluble compounds and preferentially dissolve into water at the oil-water contact. The result is that these aromatic compounds often move forward ahead of the oil phase of the hydrocarbons and can be used as a proximity to pay indicator. In other words, if these aromatic compounds are plotted versus depth and detected at sufficient concentration and the zone is obviously not a hydrocarbon zone, this can often indicate a close proximity to a hydrocarbon zone. We'd like to thank you for viewing our petroleum stratigraphy presentation. If you would like more information, please contact Rick Schreinemakers in our Houston office at area code 281-782-8914, or you may contact him at the email address on this screen. Thank you.